The topic that we're going to discuss today is Euclid division lemma from the first chapter, number systems. How many of you like numbers? Whether you like numbers or hate numbers or simply scared of it, you will soon start loving it because I'm going to make it very easy and interesting and going to happen very soon. So we will start with something called Euclid division lemma. It may be confusing, it might sound complicated, but it's actually very, very simple. It's got everything to do with divisions of integers. Let's look at a real life example first. Let us assume that there are 7 apples. Take 3 at a time and put it into a boxes. So there will be 2 boxes and 1 apple will be left out. Now, how will you represent this particular scenario into divisions? It's very simple using division, which all of you know. That is 7 divided by 3. We will get a quotient equal to 2 and remainder equal to 1. That is 7 equal to 3 into 2 plus 1. Here, the 7 is called the dividend, 3 is the divisor, 2 is a quotient, and 1 is a remainder. Now, instead of 7, 3, 2, and 1, if we replace it by a variable, for example, if I replace 7 by A, instead of 3, take B, instead of 2, take Q, and instead of 1, take R, we have A equal to B into Q plus R. This is same as dividend equal to divisor into quotient plus remainder. This generalized using variable is called Euclid division lemma. Let us try to understand by the definition of Euclid division lemma. Given 2 positive integers A and B, then there exists unique integer Q and R which satisfy the condition A equal to B into Q plus R, where R is greater or equal to 0, less than B. You should always remember that the remainder R should always be less than the divisor and greater or equal to 0. Let us go back to our previous example. If the number of apples and the number of apples in each box are fixed, then the number of boxes is fixed and the number of apples left out is also fixed. That is why there exists a unique integer Q equal to 2 and R equal to 1. That is only one set of solution will exist. Let us try to understand more by solving some of the questions. Let us take the first question. Find the HCF of 78 and 980 using Euclid division algorithm. Here, 980 is greater than 78, so we will take A equal to 980, B equal to 78. Applying Euclid division lemma, we have 980 will be equal to 78 into 12 plus 44. Here the remainder, 44 is not equal to 0. We will proceed until and unless we get the remainder equal to 0. Applying Euclid division lemma, taking 78 as A and 44 as B until R equal to 0. We have 78 equal to 44 into 1 plus 34. Following the same procedure again, we have 44 equal to 34 into 1 plus 10. Here the remainder equal to 10. Following the same procedure again, we have 34 equal to 10 into 3 plus 4. Again, 10 equal to 4 into 2 plus 2. At last we have 4 equal to 2 into 2 plus 0. That means the remainder becomes 0. As we see, the remainder has become 0. Therefore, the proceeding further is not possible. And hence, the HCF is the divisor B left in the last step, which is in this case is 2. We can say that the HCF of 980 and 78 is 2. Let us take another example. Find the HCF of 81 and 675 using Euclid division algorithm. Here, 675 is greater than 81, so we will take A equal to 675 and B equal to 81. Applying Euclid division lemma, we have 675 is equal to 81 into 8 plus 27. Here the remainder is not equal to 0. Applying the Euclid division lemma, taking 81 as A and B equal to 27, we have 81 will be equal to 27 into 3 plus 0. Here the remainder becomes 0. We cannot proceed further as the remainder becomes 0. According to the algorithm, in this case, the divisor is 27 and hence the HCF of 675 and 81 is 27. For your homework, I would like everyone to solve the following questions. Use Euclid division algorithm to find the HCF of 135 and 225. The second question is 196 and 38,220. And the third question is 867 and 255. Let us try to solve more examples using Euclid division's lemma. Let's take the first question. So that any positive odd integer is of the form 6 cubed plus 1 or 6 cubed plus 3 or 6 cubed plus 5, where q is some integers. Here what we're going to do is we're going to show that every positive odd integer is of the form 6 cubed plus 1 or 6 cubed plus 3 or 6 cubed plus 5. So let us assume that A is any positive odd integer and B equal to 6. Therefore, by Euclid division lemma of A and B, we have A equal to 6 cubed plus R, where R is greater or equal to 0, less than 6. You should remember that R is always less than the divisor, and R is an integer. That means R can be 0, 1, 2, 3, 4 and 5. Now, by placing R equal to 0, we have A equal to 6 cubed. By placing R equal to 1, we will have A equal to 6 cubed plus 1. By replacing R equal to 2, we have 6 cubed plus 2, and so on. At last, when R equal to 5, we have A equal to 6 cubed plus 5. Thus, A equal to 6 cubed or 6 cubed plus 1 or 6 cubed plus 2 or 6 cubed plus 3 or 6 cubed plus 4 or 6 cubed plus 5. Out of these, 6 cubed plus 2, 6 cubed plus 4 are even numbers. But the question wants us to solve or wants us to find out only for the odd integers. So the possible odd integers will be 6 cubed plus 1 or 6 cubed plus 3 or 6 cubed plus 5 are the form of any positive odd integers. For your homework, I am giving one question, that is, so that any positive odd integer is of the form 4m plus 1 or 4m plus 3, where m is some integers. I hope everyone will understand the Euclid division lemma. Thank you very much.